For the next two video segments, we are going to consider the problem of heat transfer through a fin. Basically, we will try to look at solution of two types of ordinary differential equation systems. In this video, we will cover one of the problem types, and in the next video, we will cover the other problem type. Now, do not be worried if you cannot get it all. What I'm trying to do through this video segment is only to try and introduce you to the problem type, make some progress with analyzing the mathematical model and bringing it to a form that will be acceptable by Matlab. And then I will also show how a typical code is written to solve these classes of problems. So don't worry if you don't get it all. We will look at these topics in great detail later, and we will look at many more examples so that your learning of these concepts will become strong. With that introduction, let me just mention about fins, right? So basically, heat transfer occurs across surfaces. If you have a hot fluid or a hot object that needs to transfer heat to a cooler body, then a certain heat exchange area is required. So the heat transfer is proportional to the area available for heat transfer. More the area, more the heat transfer. So to enhance the efficiency of heat transfer, what people do is they kind of design fins. So this is a fin. So in this example, this is a fin. All right. So in addition to this slab, right, which has a heat transfer area, you can increase the area available for heat transfer by constructing this kind of a fin. All right, this is called a planar fin. So it makes more heat transfer area available so that the heat transfer efficiency can increase. This is an example of a cylindrical fin. So this, right, this kind of a thing that you see around, that is a cylindrical fin. This cylindrical fin serves to increase the area of heat transfer and therefore increase the heat transfer. So at this stage, if you have not done a course on heat transfer, you just understand that fin is an object that is used to enhance the heat transfer. Now you can write a heat balance equation for this fin. All right. So if you consider this planar fin, you can write a heat balance. We are going to focus on the fin. The base of the fin, right, which is attached to the slab, the base of the fin is at a temperature T naught. And the other end of the fin that you see here, this face of the fin, is at a temperature T infinity. So that would be, let's say, the ambient temperature. So the base of the fin is at T naught. The end of the fin is at T infinity. And the fin is of length L. The fin is of width W, as you see here. Because this is a metal, let's say, heat transfer is going to happen by the process of conduction. So conduction is one mechanism through which heat transfer occurs. And conduction is characterized by this thing called K, which is called the conductivity coefficient. So conduction happens in this metal element. That's how heat flows within this metal element. But the heat transfer from the fin to the outside fluid or outside air, which is at a temperature T infinity, is going to happen by convective mechanisms. Convection is a heat transfer mode in which you have a solid liquid or a solid gas kind of an interface. So across solid liquid interface or solid gas interface, you will have convective heat transfer. Within a metal, it is going to be conductive heat transfer. Between a metal and a gas or liquid, the heat transfer is going to be by convection. So the convective heat transfer coefficient is denoted as H. So this is the convective heat transfer coefficient. This is the conductive heat transfer coefficient. This is the convective heat transfer coefficient. And these depend on a variety of parameters, right? For example, the kind of metal, the temperature, all that will determine what these heat transfer coefficients are. What is the fluid when we talk about convective heat transfer, etc. In any case, convective heat transfer coefficient is H, and the convective heat transfer occurs through this perimeter P. All right. So these are some of the system parameters. If you write the equation for heat transfer through this fin at steady state, assuming the mechanisms of conduction and convection. So this is the heat that transfers by conduction. This is the heat that transfers by convection. So whatever heat comes into the fin via the conductive process is transferred via the convective process to the fluid surrounding the fin. All right. So the conductive heat transfer equates to the convective heat transfer. So that's the equation that governs the heat transfer through a fin. Now let's assume that K, the conductive heat transfer coefficient, and the area for conductive heat transfer are constants. We also assume that the convective heat transfer coefficient, this perimeter P, and the temperatures T naught, which is at the base of the metal fin, and the ambient temperature T infinity, or the temperature of the fluid T infinity, remain constant. Since K and A are constants, we can take it outside of this derivative, and we can write the equation as Ka. Then you have d by dx of dt by dx minus hp t minus t infinity is equal to 0. And then we realize that d by dx of dt by dx is nothing but d squared t by dx squared. And you have Ka minus h times p times t minus t infinity is equal to 0. So just recognition of the fact that Ka are constant, you can take it out, as well as the fact that d by dx of dt by dx is nothing but the second derivative, d squared t by dx squared. I can write this expression. And then you divide throughout by Ka. When you divide throughout by Ka, you get d squared t by dx squared minus hp by Ka t minus t infinity equals 0. So you can see that a lot of effort is spent in taking the problem, simplifying it, and putting it in a form that is appealing to engineers, as well as puts it in a form that Matlab can solve it. So that is where a lot of effort that I'm describing goes. So most of the things that I'll be describing here are concerned with that, just organizing the equation and putting it in a form that Matlab will accept. Now, what I'm going to do is, I'm not even happy with this form, right? Of course, we can always solve it in this way, but we can go for a little more representational elegance. So I'm going to define a dimensionless temperature theta as theta is equal to T minus T infinity by T naught minus T infinity. So here, if you look at the equation, X is the independent variable, T is the dependent variable. And all we are trying to do is to solve T as a function of X. This is what we are trying to solve. So we want to write the dependent variable as a function of the independent variable. I'm going to define this new dimensionless parameter theta, which is the temperature at any position T minus T infinity, the ambient temperature, divided by T naught, which is the temperature at the base of the fin, minus T infinity. So both the numerator and denominator will be in temperature units. So if you take the ratio, you will get a dimensionless quantity, which is theta. So note that T is the temperature at any point on the fin. All right. T0 is the temperature at the base of the fin that is attached to the metal wall. T infinity is the temperature of the fluid, or the ambient temperature, that is the air surrounding the fin, if air is the fluid. So this is one dimensionless parameter we introduce. The other dimensionless variable we introduce is psi. Psi equals x divided by L. X is the position from the base of the fin, right? The base of the fin is counted as x is equal to 0. The other end of the fin is at x is equal to L. So x is equal to 0 is the base of the fin. X is equal to L is the tip of the fin. And we are defining this new variable psi as x by L. So psi will go from 0 to 1, because at x is equal to 0, psi is 0 by L, which is 0. And at the tip of the fin, x is equal to L, therefore psi will be L by L, which will be equal to 1. Again, at the base of the fin, T will be equal to T naught. Therefore, at the base of the fin, right, that means at psi is equal to 0, which is the base of the fin, theta will be equal to 1. So these are things that have to be borne in mind. Now, if theta is given by this expression that you see here, if theta is this, then I can write d theta as, right, the derivative of theta as d theta is equal to 1 by t naught minus t infinity, because this is a constant, right? 1 by t naught minus t infinity d of t minus t infinity, right? So if you take d theta, it is going to be equal to 1 by t naught minus t infinity times d t minus t infinity. But since t infinity is a constant, dt minus t infinity is just going to be dt, because t infinity is a constant. Therefore, we can write this first equation. D theta is going to be 1 by t naught minus t infinity dt. So once we have got equation 1, what I'm going to do is I'm going to apply the differential operator on both sides of equation 1. So I'm going to write d of d theta is equal to d of 1 by t naught minus t infinity dt. So d of d theta becomes d2 theta. D of 1 by t naught minus t infinity dt will be 1 by t naught minus t infinity, because that's constant, times d of dt, which will become 1 by t naught minus t infinity d2t. So that is what you see as equation 2. Then if psi is equal to x by L, if psi is equal to x by L, I can write x as psi times L. And L is a constant. Therefore, dx will become equal to L d psi, because L is a constant. Therefore, dx will be equal to L d psi, which becomes equation 3. Then if I square both sides of equation 3, I'm going to get dx squared as L squared d psi squared. All right. So equation 4 is also understood. Now, therefore, what I can do at this stage is, if you accept equations 1, 2, 3, and 4 based on our definitions of the dimensionless parameters, I can replace d2t by dx squared with this, because d2t is going to be t naught minus t infinity d2 theta. Dx squared is going to be L squared d psi squared. Therefore, d2t by dx squared is going to become this, t naught minus t infinity by L squared d2 theta by d psi squared. And then you have minus hp by ka, and t minus t infinity is going to be t naught minus t infinity multiplied by theta, because this will go into the numerator there. So t minus t infinity is going to be t naught minus t infinity multiplied by theta. So which is what is written here. So t minus t infinity becomes this. So this equation is also justified now. Now t naught minus t infinity appears in both the terms there. So I can divide by t naught minus t infinity throughout and also multiply the equation by L squared. So when I do that, that means multiply all terms in this equation by L squared by t naught minus t infinity. When I do that, this equation reduces to d2 theta by d psi squared minus hpl squared by ka times theta is equal to 0. So this equation under these definitions of the variables will become this. Please note this equation is interesting because you just have one parameter now. So all of these things can be grouped into a single parameter. We can call this, for example, as m squared, something like that. The other thing is both the dependent variable theta and the independent variable psi are dimensionless quantities. So these offer huge advantages in the mathematical analysis. This equation is what we started with by balancing the convective heat transfer with convective heat transfer for the fin at steady state, and we use this dimensionless variables to bring it to this particular form. This is what we saw in the previous slide, and this is a second order ordinary differential equation because the highest derivative is the second derivative. So from this equation, if you want to get theta, the dependent variable, as a function of psi, the independent variable, to go from d2 theta by d psi squared to theta, we have to do two integrations, right? So the first integration will take us from d2 theta by d psi squared. When you integrate it once, you can get d theta by d psi. When you integrate d theta by d psi, when you integrate it, you're going to get theta. So we are after theta. Therefore, we have to perform two integrals because the highest derivative here is the second derivative. So when you do two integrations, you will introduce two integration constants. To solve the problem, a second order ordinary differential equation, we would need to specify two conditions so that the constants of integrations or the integration constants can be obtained without any ambiguity. So two conditions are required. If you have the highest derivative to be a first order derivative, then you require only one condition to get the integration constants. If you're solving a fourth order ordinary differential equation, then you would require four conditions to be able to find out the integration constants and to obtain the complete solution. So here, since we are doing a second derivative or a second order ordinary differential equation, we require two conditions to solve the problem. And that is what differentiates two classes of problems. The two conditions can be any two legal conditions that are specified. So if you specify the conditions in one way, you get what is called the boundary value problem. That means if you specify one condition at x is equal to 0, which means that psi is equal to 0, and one condition at x is equal to L, that means that psi is equal to 1, then this is called a boundary value problem because you're specifying the temperature at the left boundary and you're specifying the other condition at the right boundary. At one condition you specify at psi is equal to 0 and the other condition you're specifying at psi is equal to 1. So you're specifying the conditions at two different parts of the problem. One at one end, the other condition at other end. So this is called a boundary value problem. If you had specified both the conditions at psi is equal to 0 or x is equal to 0, then that would be called the initial value problem. So we are presently going to look at the boundary value problem, and in the next video segment we will look at the initial value problem. So here one condition is given at x is equal to 0, that means that psi is equal to 0. The temperature is specified as T naught. So when you put T is equal to T naught minus T infinity by T naught minus T infinity, that means theta is equal to 1. So T at x is equal to 0 becomes theta at psi is equal to 0. And the value of theta is going to be equal to 1 because when you put T is equal to T naught here, you're going to get theta is equal to T naught minus T infinity by T naught minus T infinity, which is going to be equal to 1. So that transforms the first condition in terms of the new variables theta and psi. Now, when you come to the second boundary condition that is specified, T at x is equal to L is T infinity. So x is equal to L is nothing but psi is equal to 1. Temperature is nothing but theta in the new scheme of things. So this is going to be equal to T infinity. T infinity means if you put T is equal to T infinity, you have T infinity minus T infinity by T naught minus T infinity. So that's going to be 0 by T naught minus T infinity, which is going to be 0. So theta at psi is equal to 1 is 0. That is the second boundary condition in terms of the new variables. So what we are trying to say overall is, for this problem, we started with this as the governing differential equation, which captures the mechanism of conduction and convection. And to solve this problem, these were the two associated conditions. The temperature at the base of the fin was specified to be the temperature symbol T naught. The temperature at the tip of the fin was specified to be T infinity. Then we introduced this transformation of variables to introduce the dimensionless temperature theta and the dimensionless position psi. So we use these two definitions, and using the equations 1 to 4 discussed in the previous slide, we were able to reduce this differential equation into this form. And we are now able to transform the boundary conditions from the original variables in terms of the new variables like this. So this becomes our new problem. So this is our new problem, as I said. And for illustration purposes, I'm going to just let HPL squared by Ka to be equal to 4. So this number is going to be equal to 4. Then we can write d2 theta by d psi squared minus 4 times theta is equal to 0, with these two to be the boundary conditions. At psi is equal to 0, theta equals 1. At psi is equal to 1, theta equals 0. And then we can solve it using Matlab. The commands are bvp init and bvp4c. These two commands can be used along with the plot command to get the solution to this particular problem. I'll show you the code in a short while. Now, this is something we have seen many times so far as the governing equation and the associated boundary conditions. We still need to prepare it for implementation in Matlab. Okay, Matlab does not like higher order ODEs. It does not like terms like this. So it only accepts equations, ordinary differential equations that have first order ODEs. So it does not like higher order ODEs. So whenever we have a problem that involves second derivative, third derivative, etc., we have to convert that ODE into a system of first order ordinary differential equations. Matlab only accepts systems of first order ordinary differential equations. Okay, so this is a key point. Higher order ODEs need to be converted to a system of first order ODEs. So the trick is this, and we will do a lot of these problems later, so don't worry, but just get used to the trick. So I'm going to define a new symbol z1, right? This means is defined to be theta. So the new symbol is nothing but the dependent variable itself. So in this problem, the dependent variable is theta. Therefore, the first symbol that we define is going to be equal to theta. Z1 equals theta. The second symbol we introduce is Z2. So since the highest derivative is second order, we will be introducing two symbols. One symbol is Z1. The second symbol is Z2. Z2, which by definition is dz1 by d psi, also becomes equal to d theta by d psi. So I can turn this equation around and say dz1 by d psi is equal to z2. So this becomes our first ordinary differential equation of order 1. Now let's go to the original equation. d2 theta by d psi squared minus 4 theta is equal to 0. We don't like this second order derivative. We like it, but Matlab doesn't accept it. So we have to do something to it. Please note that d2 theta by d psi squared is nothing but d by d psi of d theta by d psi. D theta by d psi by our definition is equal to z2. Therefore, d2 theta by d psi squared is nothing but dz2 by d psi. Just following these definitions consistently. So I'm able to express the second derivative in terms of first derivative but involving a new symbol. And this is okay because z2 is already dz1 by d psi and dz1 by d psi is d theta by d psi. So we are basically cheating Matlab, right? So we are taking the original second derivative and replacing it by a first derivative with the symbol, right, being z2. So d2 theta by d psi squared is the same as dz2 by d psi. So I can replace d2 theta by d psi squared by dz2 by d psi. Minus 4 theta is going to be minus 4 z1 because z1 was defined equal to theta. So dz2 by d psi minus 4 z1 is equal to 0, in which case you can write dz2 by d psi is equal to 4z1. So this is the first ODE, this is the second ODE. Both ODEs are of first order, which MATLAB likes and accepts. Please note a second order ordinary differential equation has become two first order ordinary differential equations. So if you have a nth order ordinary differential equation, by this process we can reduce it to a system of n first order ordinary differential equations. So one nth order ODE can be written as n first order ODEs. That's the idea. All right, so that is exactly what we have done here. Therefore, our original problem, which was something, got transformed to this ODE, which has now become this. Two ordinary differential equations of first order replacing the second order ODE. So this is what it is in terms of new symbols. And our conditions were theta at psi is equal to 0 is 1. What is theta? Theta is nothing but z1 according to our definition. So z1 at psi is equal to 0 equals 1. So this becomes this, right? In other words, this becomes this. And the second condition was theta. Theta is nothing but z1. So z1 at psi is equal to 1 is equal to 0 as given in the problem. So our new problem is this. Now it is in a form that is acceptable by MATLAB. So all that we did so far, right, was to take the original problem, introduce new symbols, and write it consistently in a simplified form like this, and also to get it ready for MATLAB implementation by converting the second order ordinary differential equation into two first order ordinary differential equations with the associated boundary conditions. So we are really after symbol z1 because we are after theta, and theta is nothing but z1. We are not that worried about z2. Though we will calculate both z1 and z2, our main interest is the symbol z1 because z1 stands for theta. And we are interested in solving for theta as a function of psi. Therefore, we are interested in solving z1 as a function of psi. So when you come to the MATLAB code, this is what you do. So first, you initialize the solution. That means you give a guess for the solution. You do it using this built-in function called BVP init. So we know psi goes from 0 to 1. So you break it into this domain, right? So you start at 0, end at 1, and you go in steps of 0.01. So the domain is psi is equal to 0, 1. So 0 is the left boundary and 1 is the right boundary. You break this 0 to 1 into 100 segments. All right. And then you try to find out the value at each of those points. That means the solution at psi is equal to 0, psi is equal to 0.01, psi is equal to 0.02, psi is equal to 0.03, all the way till psi is equal to 0.98, psi is equal to 0.99 and 1. So we are breaking the domain of the problem psi that goes from 0 to 1 into 100 segments by specifying the step size of 0.01. And we are saying as a guess that z1, right, Z1, that symbol, we are expecting its value to be 0.5 in the domain. For Z2, we are expecting it to be minus 0.25 throughout the domain. That is our guess. But the solver that we are going to introduce shortly will process this guess and take us to the correct values. And hopefully our guess is reasonably right, because the solver, the boundary value problem solver, BVP4C, what it is going to do is it is going to apply a Newton type method to solve the equation, and therefore it needs a initial guess, right? The Newton method always needs a guess, as we shall see. And we discussed this when we talked about solution of a single nonlinear equation. We talked about the Newton method. It requires a good initial guess. So we are just providing these to be the initial guesses. This is for symbol Z1. This is for the symbol Z2. What I'm trying to say here is this is psi, and let's say this is Z1. Psi goes from, let's say, 0 to 1, right? This is psi is equal to 1. This is psi is equal to 0. So I'm expecting Z1 to be flat at 0.5. So this is what I'm expecting. And for Z2, I'm expecting Z2 to be minus 0.25 throughout. This is psi is equal to 1. This is psi is equal to 0. So Z2 is going to be minus 0.25. That is what I'm expecting throughout. So this is my initial guess. All right. So once I have provided the initial guess through BVP init command. So BVP init, the first input argument is the domain and how the domain must be broken into segments. The second thing is the initial guess for the symbols in the problem. So the symbols are Z1 and Z2. So for Z1, I specify 0.5 to be my initial guess, and for Z2, I specify minus 0.25. So once we have this, then I'm able to call the solver. The solver is BVP4C. So to the solver, these are the input arguments that I have to give. I have to tell it what is the name of the function file that contains my ordinary differential equations. What is the name of the function file that contains my boundary conditions, the two conditions. And I should also give the initial guess, right? That initial guess is this sol init. So sol init, which is an output argument of BVP init, which is an output of BVP init function, that sol init becomes an input to the BVP4C function. So BVP4C is a built-in function that solves the boundary value problem given the ordinary differential equations, given the boundary conditions, and given the initial guess. So once we get the solution, we can plot it like this. Once we get the solution will be in the variable SOL. So I'm going to plot sol.x. This will contain the psi values. Sol.y 1 comma colon, right? That will contain the Z1 values. So sol.y, right, will look like this. The first row of sol.y will contain Z1. The second row of sol.y will contain Z2 because this problem has only two symbols, Z1 and Z2. So sol.y will have two rows. The first row will have Z1 and the second row will have Z2. I'm interested in Z1 because Z1 is equal to theta. Therefore, I'm asking it to plot sol.y, the first row and all columns in the first row. That means the entire first row, which contains Z1 values. That means theta values. So I'm asking it to plot it in black color. And then I can label the x-axis and y-axis using commands x label within single quotes whatever I want to put there, and y label within single quotes whatever I want to put there. So if you want to show Greek symbols in the graph, you can put backslash and psi to print psi. If you want to print theta, you say backslash theta, it will show theta on the graph. All right, so this is for plotting once I get the solution, SOL. Now I have to specify now the ordinary differential equations and the boundary conditions. All right, this may look daunting right now, but you will see it is quite easy. Once you practice a few problems, this is going to be quite easy. All right, so you have a sol in it, you call BEP4C, and then you write the function file that contains the ordinary differential equations. You write the function file that contains the boundary conditions, and then you plot the results. It's quite easy. All right, so how do you write the ODE files? So you say function, let's say dz dx, some variable dz dx. So I'm saying it's like dz d psi, if you like, but we don't have psi etc in the Greek symbols in Matlab. Therefore we just say dz dx is equal to fin ode, because this is the name I've given it here. So this name and this name must match. So fin ode brackets x comma z. So x is the independent variable and z is the dependent variable, semicolon. Now dz dx1, so I'm saying the first derivative, right? The derivative dz by dx1. So basically I'm saying this dz1 by d psi. That's what I'm trying to say here. Dz dx1 means dz1 by d psi. What was that equal to? It was equal to z2. So I'm going to say here is equal to z of 2. Then semicolon. So we have taken care of the first ODE. Now when we come to the second ODE, we are looking for writing dz2 by d psi. So dz2 by d psi, we are going to write it as dz dx of 2, right? So of 2, right? So dz dx of 2, the second symbol, derivative of the second symbol, that is going to be equal to, if you remember, that is equal to 4 times z1. So it is going to be equal to 4 times z1. Done. Then what happens is, when you write it like this, Matlab will create a row vector. So it will have dz dx1 here and dz dx2 here. That's how it is. But you have to provide it as a column vector. All right. So you have to, when you come out of the function, dz dx should be a column vector. Therefore, I say dz dx is equal to dz dx transpose, which will make this row vector into a column vector, albeit with the same name. All right. So the row vector will be erased and a column vector will be created. And the function file ends with end. So this completes the description of the ODE. So how many ever ordinary differential equations are there in your system, you could just adopt this idea. Please remember this order. It has to be x comma z. The independent variable label should come first. The dependent variable should come next. And please note the name of this function file should be exactly the name of what you have specified there when you call BEP4C. So this part is now taken care of. The last thing that we need to do is to specify the boundary conditions, right? So this is the part that describes the boundary conditions. So what we are going to say here is the boundary conditions are, if you remember, z1 at psi is equal to 0 is 1. z1 at psi is equal to 0 is 1. And z1 at psi is equal to 1 is equal to 0. These are the two boundary conditions given. So please remember, the left boundary is labeled as A and the right boundary is labeled as B in Matlab. So A corresponds to psi is equal to 0, B corresponds to psi is equal to 1. When you're talking about psi is equal to 0, we are talking about A. So Z of 1 at A. So Z1 at A, right? So it is written as ZA1. So psi is equal to 0 is the left boundary, so it has got a label A. And we are talking about the first symbol, Z1. Therefore, this becomes ZA1 is equal to 1. This is what is given in the problem. So we can write this first thing in Matlab notation as ZA1 minus 1 is equal to 0. That becomes the first boundary condition. ZA1 minus 1 is equal to 0. Now when you come to the second condition that is specified in the problem, we are talking about psi is equal to 1. Psi is equal to 1 means the right boundary, which means B, label B. So we are still talking about Z1 but at B. So we will write ZB of 1. ZB, because it is about psi is equal to 1 and the symbol here is 1. So ZB of 1 is equal to 0. This is what is given in the problem statement. So the second boundary condition becomes ZB1 is equal to 0. So this is what it is. So to define the boundary conditions of the problem, please note fin BC is the name that I've given here when I call BVP4C. So that will be the name of this function. ZA and ZB, don't change this. That can just be ZA and ZB. So the output argument of this function is residual, RES. So we want to make these numbers 0. That's called the residual, right? So when the problem is solved correctly, these boundary conditions should be satisfied, which means the right hand side should be equal to 0. So we want to make the residuals into 0. This is the first line for the boundary conditions part of the solution in Matlab. So function space res within square brackets is equal to fin bc, which matches the name that is given at the top, brackets za comma zb. And we can write inside res exactly the same variable that's used here. Res is equal to square brackets open za1 minus 1, za of 1 minus 1, which is this part. The right hand side is 0. Please ensure that. Semicolon. Then the second boundary condition is ZB1 is equal to 0. So it's equal to 0. So no problem. Just write the left hand side ZB1. And then end the residual array and semicolon, right? That we put at the end of every MATLAB command. And then it ends with END. Every function file should end with end. So all of this that you see here is put in a single M file. Basically, it contains 4 parts. Initializing using BVP init and solving using BVP4C. Once you get the answers, this is plotting the results part. So this segment plots the results. But to solve it, you have to tell MATLAB what is the ordinary differential equations that you need to solve. For this system, these were the 2 first order ordinary differential equations that we needed to solve. So we implemented that. And we also have to tell what is the boundary conditions that should be obeyed. So this part does that. So basically, it's a few lines of code. Okay, and it can solve more powerful problems than this. And this code, when executed, will generate this graph for us. This is how theta changes as a function of psi. And all these codes are available in OWL for you to take a look. Now, please note before leaving this particular video segment, this is the domain starting from psi is equal to 0 to psi is equal to 1. The left boundary to the right boundary. The left boundary is labeled A, the right boundary is labeled B. So some conditions for the problem are known here. Some conditions of the problem are known here. So in this case, we had a second order ODE, so we needed 2 conditions. One condition was given here, other condition was given here. So therefore, we have to solve the problem for all the other internal locations, right? So we do not know what is the value of theta or d theta by d psi at these internal points. In fact, we do not know d theta by d psi at the boundary points also. We are given theta at psi is equal to 0 and theta at psi is equal to 1. So there are many things that we need to fill in. We do not have any information for the points inside. So this is what is called a fill in the blanks problem. All right, the ordinary differential equation holds throughout the domain from psi is equal to 0 to psi is equal to 1. The boundary conditions holds only at psi is equal to 0 and psi is equal to 1 as stated in the problem. So we need to fill in the blanks in a way that is consistent with the governing differential equation that governs the heat transfer mechanism within the fin. So that has to be consistent. So the boundary value problems are fill in the blanks kinds of problems. So we have taken a tour of the boundary value problems. It may be a bit hard for us to start with, but the idea here is to get used to it as early as possible. So if you really break it down, if you really unpack it, all you have is you have an ordinary differential equation that will be given to you along with the conditions required to solve the problem. In this case, you will be given the boundary conditions. So you may want to convert the given equation using some dimensionless variables into a more simpler form. Or minimally, what you need to do is you have to convert any higher order differential equation into a system of first order ordinary differential equations so that MATLAB will accept it and solve it. Once you do that, it's a matter of writing this code. And even in this code that you see on this slide, you may have to change only 3 or 4 things, not more than that. So we will get enough practice when we solve the boundary value problems in great detail. Thanks for your time.